Hello, my name is Ram Rao, and today I'm going to show you how to design a rectifier circuit which can convert 110 volt or 240 volt AC main to 5 volt or 7 volt DC. Like we have adapter which has same circuit like rectifier circuit, like a step down transformer to convert the utility voltage is like 110 volt in USA, and the frequency is like 60 hertz. And for our to for for to charge our phone, we need DC source. So like for our iPhone, like Android, for that one we need like 5 volt to 7 volt supply voltage as DC volt to charge them. So let's go to design that circuit. So let me share my screen. So for that one, here is, so I have done that project, which was my final project for power electronics. The course title is 440. Like it's also high level, like 540 for graduate students. And that was like combined. And it's more like power supply design. So here there will be 3 design, like a step down transformer, then full wave rectifier circuit, then I will be using a buck converter. So the background for this project is this project is like a highly open-ended design. So you don't need to like only use like buck converter. You can also use like boost converter. Maybe you can use buck boost converter. So here in this design, I'm going to use a buck converter. So the design requirements are input voltage. So we have 110 volt to the range 110 volt to 240 volt, and at frequency 50 hertz to 60 hertz. Because this voltage, like 110 volt for our utilities here in USA, we have 110 volt and 60 hertz, and in Europe, in Asia, we have like 200. Over there, it's like 220 volt over there. Like I am in Nepal, in India, like we have like 220 volt for utilities and 50 hertz as a source frequency. So the design goal is to convert that input voltage to DC. So here, yeah, uh, uh, we can either design a circuit to get 5 volt output, or here my GID is like 7 volt. I have like 2, so it's like I'm designing to get 7 volt DC with this fluctuation like 1% plus minus, with less than 0.01 volt ripple current. And this is the 2 ampere load. So N is my last digit in my GID, which is 2. So 5 plus 2 is 7. So for that design, there is like we need to use isolated. The source need to be isolated. For that one, we need to use some kind of switching power pole supply circuit, like DC to DC converter. So here I'm using DC to DC. It's called buck converter. So procedure, like so it's, since it is open design, so you can use either like any buck boost or boost only or buck any one to get a 5 volt. So let me open my LTS Spice. So here is my LTS Spice. So I have already built the circuit. So this is the circuit. So I'm going to explain every part by each time. So this is my source. This is AC source. Right now I'm using 110 volt RMS, which is equal to 155.6 volt as a peak, and it's at 60 hertz frequency. So I have like a resistor value which is 1 ohm, and I'm designing. Let me show you like let's go through one by one. Let me disconnect this circuit. So right now I just have like, so this is just a step down transformer. So to build a step down transformer, suppose here my goal is to get 15 volt AC, 15 volt AC from 155.6 to 15 volt. To get that one, we need to choose the inductance value for that one. Since we know like uh, for transformer, the ratio of turn ratio is directly proportional to voltage in primary. Suppose like primary voltage divided by secondary voltage, which is equal to number of turns in primary divided by number of turns in secondary. So let me find the ratio. So 155.6 to get a 15 volt. So the ratio is like the turn ratio is like almost 10.4 in primary, and in secondary it's like 1. And as we know, the relation between inductance and the turn ratio is inductance is directly proportional to a square of turn number of turns. So just by squaring that ratio, we can get 107.6 is to 1. So here I have inductance 108 millihenry, and this one is just 1 millihenry. It's 1 millihenry, and I'm assume the resistor, the load resistance like 2 ohm. Let's see, like for 2 ohm, how much we get. Let's run this circuit, then we can check everything. So let's put over here. This is the input voltage. The peak should be 155.6 volt AC at 60 hertz frequency. So 60 hertz is how much? Like 1 divided by 60. The time period should be like 16.7 millisecond. The time period is 16.7 millisecond. So here we can see here, right? This is the one wave. So from here to here, it's almost one period. It's one period which is equal to 16.7 millisecond. So let's measure the cursor, measure the input voltage. The input voltage we have over here 155.412, right? And let's check the output voltage, how much we get on. So here, let me choose just one cursor. We just need one cursor. So let's get over here. So we have 15.137, which is our design. I mean, our required. I want to step down 155.6 volt to 15 volt AC. So right now we check this one. We are getting that one. Let's connect this circuit. So let's connect this circuit. all down. Let's connect this again by. Now that circuit is connected, so we can go one by one. So right now I'm not going to connect the whole buck converter. This is buck converter circuit. So what I'm going to do, I'm going to disconnect the buck converter circuit from here. Right, I disconnect buck converter circuit here, and I'm going to put one ground over here. And now run this circuit. Time is too small. Let me see. Let me remove that ground. Now run this circuit. Time is still too small. This is the circuit. Maybe we can disconnect from over here. Let me put over here. Remove that one. And put one ground over here. Let's run this circuit. Analyze the time step to a small time. On top with IRF G4 external remote. Oh, I guess. So that circuit is not connected. These are connected. Oh, these are. Oh, maybe these are connected. That's why we are getting. Let's check over here. Is that? There's. Oh, because these are also connected. That's why we are getting like. So we need to remove the whole thing. I mean, because this whole circuit is running. That's why we have this problem. So what I'm going to do, I'm just going to back up. Now I'm going to run that circuit. It's over here, it's pulse. I don't want a pulse. So this is a rectified voltage. So let's measure let's put cursor. So we have like 12.76 volt as the DC voltage. But over here we have like 15 volt. We are supposed to have 15 volt over here. I think it has two cursor. We just need one cursor. So to put over here, we have, you see, we have 13.52. You see, before when I disconnect this part, I had like 15 volt over here. But right now I don't have 15 volt over here because these diodes and this MOSFET, they consume some kind of power. That's why we don't getting like exact 15 volt. So no worry. So over here, how much we have over here? We have 12.8 volt over here. This is DC volt. So this is rectified DC voltage, 12.8. And to measure here, like here, how much we getting? Here we are getting 7 volt. You see, exact 7 volt. To get that one, we need to maintain the for buck converter. The for the buck converter, uh, the risk. I mean, the for buck converter, the output voltage is duty cycle times input voltage. So the duty cycle is nothing but it's V output voltage divided by input voltage. So here with we guess like we have like input voltage for DC buck converter like 12.34, and we want 7 voltage, 7 volt, which 7 divided by 12.34, which is like 56.7% on duty cycle. And here I have time period 20 and I have timer on. It's like 11.35 divided by 20, which is like 56.75, which is what we have here. That's why we are getting exact 7 volt. And this is controller over here. This is comparator. This voltage is coming over here and going over there. And this controls by voltage regulator here. It has gain of 1, which drive the gate of the MOSFET IRF G254. And here I have, sorry, let me make bigger. So here I have 100 millifarad for C1. It's polar capacitor. I have chosen 100 millifarad because if I have like suppose if I have a smaller value like 500 microfarad. So let's see how it looks like the ripple voltage. You see how much is the ripple over here? So these all are ripple. It's going from here, it's going here. These all are ripple. So it has really large ripple. Like 14 volt over here. How much is? This is almost like 5. So 14, 5 is like more than 2. It's like a lot of ripple. So for that, to control that one, I have the when I put 100 millifarad, and when you run this one, then the ripple will be really small, and the DC voltage, the DC is a straight line, mostly a straight line. Let's see this. You see? So it has, let me see, it's cursor 2. It's like 6.97 volt, the output voltage. Let's measure one more time over here. It's like 7. Now over here, from here to here, it's 7 volt. It's going like some hard somehow like lesser. We can also check the current over here. The required current we need to get like 2 ampere. When you put cursor over here, we have like 199.28, which is most close, like 2 ampere almost, which is one of the required condition for over here, like here, 2 ampere. And he also wants the circuit works properly down to a 0.2 ampere load. So for look at this one, to get a 0.2 ampere over here. So how much since we have 7 volt here, to get a 0.2 ampere, the resistance should be like 35 ohm. Let's change 35, then how it looks like the current. Let's say now we are looking for 0.2 amp, which is over here. Which is 0.2 amp. So right now I have for the load resistance, it's almost 35 ohms. So it gives the current looks like between 280 and 320, like 295 milliamp, like 0.29. Still, it's more than what we need. Or to get exact to 0.2 ampere, let's try over here how much. So right now we have almost 0.3 ampere, but we need to see the circuit works properly up to 0.2 ampere as a load current. So and we can see here like when we have like 0.3 ampere load current, the circuit works. Look at the straight line, how the straight line the current is. So that's good. Let's make this one as 55 ohms. Then when you run this one, it's about to 0.2 amp. So let me open my document which I made last week. So rectifier project, this one. So let me show you. So the requirement is we are basically converting the range. This is the range of the voltage, the AC voltage, the input voltage, which is 110 volts to 240 volts at 50 hertz to 60 hertz as source frequency. And the output is like 5 plus 2, which is 7 volt. And it should be like plus minus 1%, maybe like up or down 1%. So the main procedure is to get this goal for this design as to get a 7-volt DC from 110 to 240 volt RMS AC. So basically, we are using a step down transformer of turn ratio. As I said before, like the turn ratio, it was like so 155.6 divided by 15. So like 10.4, like what I have here, 10.4:1. To get 15 volt AC at secondary transformer from 155.6 volt peak, we need to have this turn ratio, which is basically simple procedure, like V1 over V2 equals N1 over N2. So we got this, and inductance is directly proportional to turn number of turns. So when we just square, inductance is directly proportional to a square of turn number of turns. So when we square this one, we are getting like 108:1. So I have we are using also a bipolar capacitor to stabilize the rectified voltage. So and also we are using a buck converter of duty cycle. It depends, like suppose we are not getting 15 volt exact because of the diode, because these are not ideal device and it can consume some kind of power. So with this duty cycle, we cannot get 7 volt from 15 because we are not getting 15 volt at the MOSFET. So we need to increase the duty cycle. We need to play with the duty cycle to get 7 volt. And the load, since the load current is 2 ampere and we have like load voltage, the output voltage 7, then we can calculate the load resistance, which is 3.5 ohms. The design requirement is maximum ripple voltage 0.01 volt, and filter capacitance can be calculated using this one. So this is the formula for calculating the filter capacitance, which is 500 microfarad, and inductance can be calculated as this formula, which is D into T. D is duty cycle, and this is assumed, I mean B input for the buck converter, and this is the output of the buck converter, and 2 is just dividing by 2, which is the current. The current is 2 ampere, so we're getting like 35 milliamp. We are using pulse wave for the feedback control switching, and I have also comparator like OPAMP LT1213. So the final circuit uses over here. So this is the feedback, this closed feedback circuit. This is the pulse wave generator, and feedback, the control voltage is coming over here and it's going to over here. And this is a voltage regulator. This is ideal voltage control voltage source with gain of 1, which drives the gate of MOSFET IR of G24. And this is the whole procedure. And let me go over LT spice. So right now, how much we have? We have 199 milliampere, which is almost 0.2 amperes. So we are getting this. Now what I'm going to do, let me make bigger this one. Let me move this part over here in the middle. And now we can make bigger. So right now I have some 55 ohms. So I have this. And now I'm going to change. Now I'm going to put 240 volt RMS, which is the peak value for that value of RMS is 300. Oh, sorry. 300. Let me calculate one more time. It's 100, 240 into the square root of 2. 240 into the square root of 2, which is almost 339. 339.4 for 1. And let's try with 60 hertz. Now we also, to get from this value to get a 15 volt, we are doing same procedure with this value. So 339.41 divided by 15. So this time I have the turn ratio of primary to secondary is 22.63. When you do a squaring, we are getting 511 or 512. We can put over here 512 milli. And here we have already 1 milli. So right now, and if you just want to see this guys, the input and just the step down transformer, how it works and how it looks like. I'm not, because there is no, that's why I actually gave it. So this is the input voltage, the source, the waveform of the source. The peak value should be 339.41 volt, which is peak, not RMS. So let's put a cursor over here. Let's try. It has 2 cursor. We just need 1 cursor. So the cursor 1, you see, we have 338.82. We have here also this value. Now we can try with this. The output of a step down transformer or voltage at secondary, which is 15 volt. 15 volt. You see, for the transformer, the coupling is almost, it's tight coupling. It's 1. We are assumed the transformer is ideal with perfect coupling, which is 1, K1, L1, L2. To build a transformer with inductor, we need to use these values. Now I'm going to reconnect the whole circuit. My backup. Now I'm going to simulate this circuit. So let's see what we are getting for the step down voltage. You see, since we have the whole circuit as a rectifier circuit and the buck converter, everything, especially like a rectifier circuit, that's why we are getting the only the up level of this value, like half wave. Yeah, now it's done. Let's measure the peak value. So here the peak value is 14.64 or 645, so 65. It's not exact 15 volt. Now let's measure the rectified voltage over here. So the rectified voltage is 14.9 volt. So I need to change some values over here to get. So here we are getting 14.91 volt, and to get a 7 volt at output as output, then we need to divide by this 13.91. So the duty cycle is almost like 50%. Oh, I have 20 microsecond as a period, then the timer on. The duty cycle is ratio of time on divided by time period, or ratio of timer on to time period. So we are 10.065 microsecond. Let's go over here. Now we are going to, did I change this value? Oh, we have 55. Let me make 3.5 ohm to get 7 volt. Now run this circuit. So right now we have this rectified voltage. We need to see the output voltage. The output voltage, which cursor is this? This is cursor 1, which is 6.61. Let me do one more time. How much is this guy? And this is cursor 2. So this is 6.61. How much is this guy? And this is 13.7. How much we have here? 917. We need to calculate the duty cycle. We are 13.7, 51%, 0.21. Now on this cycle. Now looks like 7 volt. So this node is for the output. Hold on. So this is for the output. This is 1. We are getting 6.8 volt. How much we are getting over here? This is 3 13.7. Response. So we need here off duty cycle. So this is the 13.7. Let me try this guy. Or 6.87. To play with this guy. Yes. So for this project, this is input voltage. So 155.6. So output voltage, which is 7 volts. And for additional waveform, step down voltage when only transformer circuit is given. So it has like this guy. It has value like 15.13. Step down voltage when rectifier circuit and buck converter and feedback circuit are present during whole circuit. It's like 13.869. Like here, it has this guy, 4.8. Let's go over here. Let's put over here. How much is this guy? That's 7.62. So we just need one cursor over here. So now it's like 7.28. Yeah, like we can make 10 point. Now we have like 7.119, which is good enough. Or maybe if you want to get exact one, like 7 volt, like just 6. Let's try this value. You see, now we have like exact 7.08 or 7.1 volt. Good, it's good enough for the requirement voltage for the design. So we can play. We can play with some values over here. Let me bring this just to middle. Let's try with 50 hertz. Same voltage, 50 hertz. So there will be nothing changed, but just the repetition. The time period will be like increased time period. For this time, the time period should be 20 microseconds, 20 milliseconds. So now we can see. So voltage will be same, exactly same, everything will be same. Just for the timing, this guy will be changed. Last time we had like 16.7 millisecond for at 60 hertz frequency time. Let's try. This is voltage is same, everything will be same. We just need one cursor. Oh, sorry. Now like 7.08 volt, which is the requirement. To see the frequency, changing frequency, we can plot the input voltage. You see, last time we had this guy. You see, the 1 period was over here, right over here, which is 16.7 millisecond. Right now, the one whole cycle, the wave is over here at 20 millisecond. So this is the period. This is the period for 20 millisecond for the frequency at the frequency 50 hertz. Everything will be same. Everything will be same. Oh my God. I can change the color. I don't like a red color. This looks better. We can put any here. So here we have the step down voltage is almost 14.54 volts. We can also check the rectified voltage, which is 13.68 volt. And we have the output voltage we have over here. We have 7.08 volt at output. We can measure the capacitor current, which will be like zero, like, which will be like a ripple. Let's measure ripple current inductor. Let's zoom it. Let's see how it looks like. So let's come. So this is the ripple. So this is the ripple one. So let's choose first and second. Sorry. And this is where we can put over here. So the peak to peak or ripple, see how much is? It's like difference like 1.94 ampere, which is almost like 2 ampere current, which is the peak to peak, which can be divided by 2. It's sort of like 1 volt, 1 ampere. So this is the ripple voltage in inductor. And we can also measure the ripple voltage in capacitor. Let's try ripple voltage capacitor. So Moses should be same. Like, oh, hold on. So cursor 1 is at minus something. And cursor 1 is 1 ampere. We need to do like 0 point something, 0.00 something. And so it has inductor current, the value is almost, which is equal to, it should be like 2 ampere. Because here we are assuming like this current should be like 0 almost. Because at a state condition for the average current in capacitor, it should be 0. So let's try the voltage over here. I'll look at how this looks like. This looks like because this is too much zoomed. Let me hold this one and let me run one more time. You know, there is still some ripple over here for this guy. You see, there is like some triangle shape, a small triangle shape. These all are ripple. It's not totally like a straight line for DC. Suppose when we zoom this guy, let's zoom it. This is some kind of, there is coming. This is how it looks like. You see, when you zoomed a lot, now it's coming the same way. You see, it's too much zoomed. So it shows that the voltage is not 100% ripple. There is still some ripple over there. It's not like totally, uh, totally, uh, it's not like there is no ripple. There is some, I mean, some little percent of ripple over there. Measure this value. I can choose two values for that one. So this will be ripple voltage for that one. Yeah. Yeah. So the ripple requirement is like 0.01 volt, 0.01 volt or 10 millivolt. Here the difference is like the ripples, it's showing 8.72, which is good enough. It's millivolts. So the design is successfully achieved, accomplished. Let's go over here. Now what I'm going to do, now maybe I can try with like, yeah, it's same thing. You can try with other values. So this is, let's measure over here. See, voltage is almost 300, the 5.37 something volt over here. How much is here? Millivolt, nano. Maybe. I don't want any values over here. So this is the design. So hope you guys understand the this design of rectifier circuit using a step down transformer, full bridge rectifier circuit, and this is the buck converter, and this is the feedback loop. This feedback loop is coming. Feedback is coming from here, and this is OPM LT 1213. It's comparator, and this is voltage regulator of, I mean, ideal voltage source, voltage controlled voltage source to drive the gate of the MOSFET IRF G24. So this is the basic design to convert 110 volt at 50 or 60 hertz, or 240 volt at 50 or 60 hertz AC to get a 7 volt or 5 volt DC. So this is the design procedure, and this is the simulated everything. It's done in LTS Spice. So I hope you guys understand this whole process of the design. And if you understand, if you like, please is saved, and so I can make another video. Next time I'll be putting one more comparator over here to control the gate of the MOSFET. That will be whole closed loop. It's also closed loop, but later I will also design another one. Thanks for watching. Bye for now.